All right, we are on to chapter 7, lesson 2. This is going to cover a lot of our other forms of energy. They all fall under kinetic and potential, but they're a little bit more specific. What I want you to do right now is to pause this lesson, go back to the weekly guide, and near the top right should be our vocabulary definitions. Open that up, you're going to need them. So I'm going to give you pause this video. I'll wait a few seconds. Then we can get going. Okay, hopefully you have that open. All right. We learned last week that there are two factors that contribute towards an object's kinetic energy. They are mass and speed. Speed is squared, so speed has a much bigger impact than mass does. But if you combine mass and speed, you can find out an object's total kinetic energy. The rule that you are going to need to know again this week is 1/2 times mass times speed squared. That's gonna come in handy in just a few minutes. You also learned last week that the two factors that contribute towards an object's gravitational potential energy, which we will often call just GPE for gravitational potential energy, the two factors are weight and height. It has nothing to do with motion. It's just strictly weight and height. And then the formula that you needed to know last week and that you're going to need to know again this week is GPE equals weight times height. All right. So we are going to combine kinetic and potential energy into something called mechanical energy. What I need you to do is pause this video, go back to the vocabulary definitions, find mechanical energy, and read its definition. Okay. This football right here has both kinetic and potential energy. It has gravitational potential energy. It has 32 joules according to this diagram because it has both weight and height. I can find the weight of a football and it's a certain distance off the ground. That ball, even though it's moving, does have weight and height, and it has 32 joules of gravitational potential energy. Well, because the football also has mass and speed, well, it also has kinetic energy. And according to this diagram, it has 45 joules of kinetic energy. Mechanical energy combines those two. So this week, for mechanical energy, we're going to add GPE and kinetic energy. So we take the 32 joules of GPE, the 45 joules of kinetic energy, we add them together. And if you look at this diagram, 32 joules plus 45 joules gives us a total mechanical energy of 77 joules. All right. So we're going to have problems where we have to add GPE and KE. All right. So here we have an example of somebody who is doing a little snowboard jump. So at the very beginning, they have zero speed. They're sitting still at the top of the hill. Their speed is zero, and that means when we find their speed in the kinetic energy formula, we're multiplying by zero, and we're going to have 0 joules of kinetic energy. We have weight and height. And so that person has 50,000 joules of potential energy. Okay. Then the sledder starts going down the hill. And so if you look at this second stage, they don't have as much weight as height anymore. They've gone down the hill. So they've lost potential energy. But they're now moving. So they have mass and speed. So now they're up to 20,000 joules of kinetic energy. So at the top of the screen, I'm asking you, what do you notice? Well, if this is mechanical energy, and we're supposed to be adding the two, in the first stage, 0 plus 50,000 equals, well, 50,000. At stage 2, 20,000 plus 30,000, we're still at 50,000 joules. All right, we get almost to the bottom of the hill before we get to the ramp. We are moving much faster. So now we have 35,000 joules of kinetic energy, but we've lost height. And so we've dropped down to just 15,000 joules of GPE. But combined, 35,000 and 50,000 gives us our consistent total of 50,000 joules in this diagram. Then the person jumps up off the ramp. They've gained height. So their potential energy, and actually, if you look at the diagram, they went from 30 to 60 off the ground. So their gravitational potential energy also doubled. It went up to 30,000. But gravity's starting to grab a hold of them, and at the top of the jump, they're not moving as fast, and so they're down to just 20,000 joules of kinetic energy. But combined mechanical energy is 50,000. Then when we get down to the bottom of the hill, our height is 0, so when you multiply by 0, you get 50,000 joules of potential energy. But we are now moving as fast as we've been in this diagram, and so we're up to 50,000 joules. Our mechanical energy is 50,000 plus 0, so 50,000 joules. So this diagram does a couple of things for us. Number one, it shows us that the calculations that we've been doing are going to be consistent for us sorry, got distracted by my cat. The calculations that we're going to be doing are going to give us a consistent answer in a diagram, and that is because of something called the law of conservation of energy. When we did mass, we had the law of conservation of mass, which was mass isn't created or destroyed. It just always goes somewhere. Well, the same thing is going to be true for energy. The total energy stays the same. In this diagram, it's 50,000. And it's just changing from one kind of energy to another. All right. So you are going to have sample problems, and you need to follow the same basic rules that we've been following, and then add our two answers at the end. So you're going to have a question that looks like this. An 8-kilogram rock, which is about 80 newtons, falls off of a cliff. At 4 meters off the ground, it is traveling at 7 meters per second. What is the mechanical energy of the rock? Well, mechanical energy is kinetic plus potential. So we have to use the rules that we did last week and then add those two answers together. So let's start off with GPE, which is weight times height. Now, out of all of these numbers, only one of them is the weight. Because weight is different from mass, mass is in grams, weight is going to be in newtons. So we have to use the 80 for our weight. For our height, we can see that it is 4 meters off of the ground, and so we're going to use that. So for GPE, for weight times height, we are going to use the 80 for the weight, because it's newtons is weight, and we are going to use the height of 4. And that means that our GPE is 320 joules. Okay, now we have to find the kinetic energy. The kinetic energy is 1/2 times mass times speed squared. That little 2/3 of a triangle in between the speed and the 2, it's called a caret. That's one way of writing an exponent. So mass is always in grams or kilograms or something like that. So we're going to use the 8 in the problem, an 8-kilogram rock. For speed, that's our meters per second, which in this problem is 7. So for kinetic energy, we have to do 1/2 times 8 times 7 to the power of 2. Order of operations, we have to do the 7 to the power of 2, which is 49. 1/2 times 8 times 49. 1/2 times 8 is 4, and that gives us 4 times 49, 196 joules. All right. This question is asking what is the mechanical energy? So mechanical energy is potential plus kinetic. So we're going to take the 320 joules from GPE, the 196 joules from KE, and add them together. And our final answer is that the mechanical energy is 516 joules. Wow. Yeah, you're going to have to do some work. All right. We're going to have other forms of energy that are going to be covered, and we're going to be referring to these over the next couple of weeks. So, nuclear energy is energy stored in the nucleus of an atom. Now, because all of these other forms of energy are just types of kinetic and types of potential, we need to kind of classify which ones these are going to be. So, looking at the definition for nuclear energy, it's energy stored in the nucleus of an atom. The stored is kind of a big giveaway that this is going to be a type of potential energy. So, nuclear energy is a type of potential energy. So, we are going to cover two kinds of nuclear energy. The first is called fission. The fission is when the nucleus of an atom splits. So in this diagram, a lonely neutron is fired at a uranium atom. After it gets through the electron cloud, it's going to hit this giant cluster of protons and neutrons that are in the middle. That's going to cause the uranium atom to split. And then when a nucleus splits, it's going to release a ridiculous amount of energy. Those splitting pieces of protons and neutrons travel and hit nearby uranium atoms, and this causes a big chain reaction of splitting atoms, the splitting nucleus of an atom, and that is going to release a overwhelming amount of energy. This process is what is used for nuclear power plants and nuclear bombs. Both of those require the splitting or fission of very large atoms, and uranium is a very good one because it's pretty unstable. So all of these protons and neutrons being held together is holding on to a ridiculous amount of energy. And when that energy gets released in the splitting of the nucleus, you get a very large release of energy. The other kind of nuclear energy is the opposite. It's called fusion. The word fuse means to join together. So, fusion is when we take smaller elements and we start forcing them together with so much energy that they actually start to combine nuclei, and that's going to give us an even larger amount of release of energy. So, in stars like our sun, these are giant fusion reactors. They are taking an element like hydrogen, which is element number one, and when hydrogens ram together with enough speed, they will actually start to make bigger elements like helium and then on up the line. This process releases energy and free neutrons. So stars like our sun release an a fantastic amount of energy because of the fusion process, which is a type of nuclear energy. So, our sun is one big nuclear fusion reactor, and that's why it can give us so much energy from over 90 million miles away. All right, I want you to pause the video, go find the definition of thermal energy, and review it. Okay. Thermal energy, according to the definition, is mostly what type of energy? Is thermal energy, if you look at the definition, mostly a kinetic or is it mostly a potential energy? Thermal energy is all about the movement of atoms or molecules. More thermal energy is more movement. So that makes thermal energy primarily a type of kinetic energy because it's all about the movement of particles. All right. For electrical energy, pause the video, go find its definition. Is electrical energy, by reading the definition, a kinetic or is it a potential? This one should be pretty easy if you're looking at the definition. It is primarily a kinetic energy, but it can be stored. We store electrical energy in things like a battery. So a battery is actually stored electrical energy. It's actually kind of a type of chemical energy, but that's for later. Okay, this is a fun one. I really like this one. Electromagnetic energy. Look at our definition. So pause the video, go find the definition of electromagnetic energy. Okay. Not all light. In fact, most light is not visible to the human eye. The human eye can actually only see a very small range of light. Um, Light travels as waves, and the human eye is designed to only see certain wavelengths. We call this visible light. So here we have what's called the electromagnetic light spectrum. If you look at all of these different wavelengths, from left to right, we have radio waves, microwaves, infrared, ultraviolet, X rays, gamma rays. All of these are types of light. The human eye can only see this tiny little band right there. That's it. So that means that the human eye can only detect less than 10% of the types of light that are out there. The difference between red light or yellow light or green light or blue light, that all comes down to how long or short of a wavelength it is. According to this diagram, the longer waves are red, the shorter waves are purple. So let's discuss a few of these as we get from left to right. First up are radio waves. These are very long waves. Radio waves are we use these waves to listen to the radio. So if you tune into the radio in your car, or if you've got a radio in your house, it is actually designed to detect invisible to our eye waves of light that are just being broadcast from antennas. So radio waves are actually invisible light waves. Microwaves are a little bit shorter in length, and these are the ones that are actually used in the microwave ovens. Microwave ovens use a invisible light wave to give energy to your food. Now, when you turn on your microwave, and you put in food, a little light bulb comes on and you can see your food spinning. That little light bulb is not helping much at all to cook your food. In fact, you can unscrew that light bulb and your microwave oven will still work because it's actually got a microwave generator inside that is blasting the food with invisible waves of light. Um, and those waves, when they hit your food particles, get them very excited and get them to move more. And we know that more movement equals more thermal energy, and that's why your food gets hotter. All right. Next up is infrared. Infrared is what is used um, for remote controls a lot. If you look at your TV remote or your stereo remote or anything like that, there's a little light. Looks like a little tiny light bulb that's there. There is actually invisible light beams coming out of that that our eyes cannot see. Um, Ask Mr. Bogdan to show you the cool way to see infrared light waves. We'll see how many people are still paying attention to the video at this point. Um, uh, Ask Mr. Bogdan to show you the infrared beams. Okay. Then we have this tiny little patch of light that our eyes can see from red to purple. All right. After that, as we continue to get shorter, we have ultraviolet light. Ultraviolet light, or UV, you may see that like on sunscreen. UV is kind of dangerous light because the shorter the wavelength, the easier it is to penetrate material like our bodies. This is why UV light is dangerous because it can actually penetrate and damage our cells. That's why UV light causes sunburn and is actually damaging our cells. Um, uh, bl- Real black lights use UV light as well. X-rays are the second shortest waves that are out there. These are so good at traveling through substances that we actually use X-ray machines to take pictures of the inside of our body. These are so when you if you've ever had an X-ray taken, they actually blasted you with a beam of light that your eyes couldn't see, and that beam of light went through you and then left an imprint on a photographic plate behind you. And then the most dangerous light waves of all are gamma rays. These are very, very high intensity, very short waves, and they are very, very destructive. I was actually watching a documentary on like the top 10 ways for the planet Earth to like be just to end all life. And one of the number one ways was actually from a gamma ray burst. If a nearby star has a gamma ray burst, which does happen from time to time, those light waves would actually blast away Earth's atmosphere, and that would pretty much end life on our planet. So yeah, gamma rays are the most destructive. And for those of you who watch like the superhero movies, like the Incredible Hulk and things like that, they often talk about gamma radiation. That's because gamma radiation is the most dangerous form of light. Okay, the electromagnetic light spectrum really deserves a lot more attention because it's just a lot really neat and fun. So I put together a YouTube playlist. The link is on the weekly guide. Worth checking out when you get some time. You're going to be pretty busy this week, but check it out. All right, pause the video. Go find the definition of chemical energy. There is a key word in that definition that helps us figure out, is chemical energy a type of kinetic or is it a type of potential? And that word is stored. Okay, so we've been looking at atoms, molecules, compounds, things like that for a while, and we know that molecules or compounds are when atoms are chemically joined. Well, when they chemically join, that holds on to a lot of energy, and so the bonds between atoms stores energy. It's a potential energy. If you look at this diagram, there's different amounts of bonds. If you look at the top left, the bond between a hydrogen and an oxygen has about 111,000 calories per mole, which is a certain amount. The bond between carbon and hydrogen actually stores a little bit less. Carbon and carbon doesn't store that much, 82,900. But up here at the top right, between carbon and oxygen, and because that's a double bond, that's holds on to a lot of energy. Anyway, where atoms join to make molecules, that those connection points store chemical energy. All right. You have to read pages 242 to 247. Most of you got well underway last week. Go get some stuff done. Check with Mr. Bogdan for your 5 questions.